Roger.
How do you hear us, Brian? Loud and clear. Boom mics in position.
Roger.
Huntsville, Alabama.
Established on 2.
NASA's Neutral Buoyancy Simulator at Marshall Space Flight Center. The Boeing Aerospace Company, in conjunction with NASA, is developing space station design concepts. Here, space station designers don suits that can be balanced underwater to simulate weightlessness. These tests contribute significantly to NASA's next major manned space undertaking. 19 tests spanning 2 months analyzed a broad range of hardware and procedures. The test's objective and focus define the space station accommodations for on-orbit zero-G maintenance and repair. The manned modules have a two-wall design. A paneled outer skin serves as a debris shield and may double as a body-mounted radiator. An inner wall creates the structural pressure shell, and sandwiched between, multi-layer insulation, or MLI. For the tests, an aluminum half-cylinder represents the study area of the space station modules. Color coding provides structural information. Blue indicates where the shield covers the pressure bottles. Red represents structural ring frames. Ribs on the surface simulate the edge of adjacent panels and allow for interference evaluation. Under designer evaluation, geometric options for panel configurations, 2 axial panels with different heat exchanger interfaces, and a curved panel that spans the 180-degree circumference of the module. External procedures are also a focus. But before anyone suits up, computer-aided design tools help model procedures. Once in the tank, those refined steps are reviewed in realistic conditions. Tether and handhold assessments help determine one-hand operations. Alternative foot restraint locations are also examined. And the designers assess the use of the station's robotic arm, called the Mobile Remote Manipulator System, or MRMS. They try it as a handling aid for panels and as an astronaut positioning device to help explore MRMS reach and envelope requirements. An alignment tool helps assess the installation and removal of panels with protruding heat pipes. The next task, removal and repair of the MLI. Designers compare using the Manned Maneuvering Unit, or MMU, with the Mobile Remote Manipulator Arm and module-mounted foot restraints.
Starting checklist. First step in MLI repair.
Another important test phase, the assessment of a voice-activated computer checklist.
How large is the diameter of the hole in inches? Give size from 2 to 5 inches.
Max 2 inches.
Talking to a computer in the control room allows astronauts to follow checklists without memorizing procedures or turning pages.
Max N.
Acknowledge.
In the unlikely event that the shell is pierced and all atmosphere escapes, astronauts in pressure suits would enter the module and repair the damage. The costly and time-consuming alternative, returning the module to Earth for repair. For internal repair testing, a metal and plexiglass cage simulates the working envelope, and equipment racks are in their normal position. To get at the damaged hull, the designers remove the racks and disconnect utilities. 3 utility locations are studied. 2 sizes of neutrally buoyant racks are removed. Single racks, 21 inches wide, and double racks, 42 inches wide. Once cleared away, an assessment of damage is made, and with test tools, an appropriate patch applied. Patch integrity will be verified later in a vacuum chamber. Conducted early in the space station program, these tests are wide-ranging enough to affect initial space station concepts and the ideas of the experts who participated. In addition to designers from Boeing, NASA EVA astronauts and former Skylab astronauts contributed to development of hardware and procedures. To further enhance evaluations, Boeing engineers directed all operations in a control room. This communications link furnished a record of comments and an opportunity for real-time procedural modifications. For documentation, underwater cameras provided continuous video coverage, and still photography furnished stop-action coverage. Boeing's findings from the neutral buoyancy tests fall into 4 areas: space station system architecture, common module external and internal, and voice-activated computers. The single most important tool, the robotic arm. It reduces weight, cost, and volume accommodations needed for EVAs, works best as a handling aid for panels, and as an astronaut positioning device. The MMU works best for inspections. 2 astronauts with both hands free are needed for servicing and repair. And 2 modules need clearance of at least 2 meters between them. Axial panels are easier to manage than circumferential, and concentrating mechanical and fluid interconnects at one end simplifies operations, reduces EVA time, and prevents panel damage from handling. Windows, trunnions, keel fittings, and umbilicals affect panel continuity and commonality. There must always be clear access to external utilities, docking mechanisms, and the like, with provisions for handholds. When panels are used as radiators with exposed heat pipes, alignment and handling tools are necessary. Module trunnions can double as support fixtures for EVA scaffolding. Careful foot positioning is essential for reach with large MLI panels, but smaller panels don't need such precise positioning. And a line of sight between the crew is an important factor in EVA productivity.
Good. It's a little out of alignment. Okay.
Because of the size of the spacesuits, at least 2 racks must be removed for access to the hull. Disconnection of utilities is easiest from the front. No special handling is needed for moving racks down the aisles. Patch procedures and tools are adequate, but could be refined.
Just hold it in place and eyeballing where it ought to be and marking it. Facts next.
Acknowledged. Fold the patch completely. Say next.
The voice-activated computer could be a significant aid for EVA operations. By eliminating unwieldy checklists, both hands would be free and on the job.
Facts, repeat.
Acknowledged. Will there be 2 subjects doing the replacement? Answer yes or no.
Yes.
The computer is ideal for space station EVAs, where rotating crews will be unfamiliar with rarely used procedures. The computer is also ideally suited for artificial intelligence opportunities.
Is the damaged area, Gash? Say yes or no.
Facts, yes.
And while 100% recognition was reported in the lab and in the pressure suit on the surface, minor technical problems produced little or no recognition once underwater. The improved microphones could eliminate extraneous sound. By testing hardware in the flight-like conditions available in the tank, Boeing and NASA are evolving hardware and concepts for the space station and looking at how they'll be used. The prolonged simulation of space provided by the neutral buoyancy chamber can be found nowhere else on Earth. Neutral buoyancy testing plays a leading role in the development of the space station and what lies beyond.